substitute in our torque 1, it's R1 M1G minus torque 2 R2 M2G equals 0. Okay, and I'm going to come up here and just erase this just to get some more room. So what we have, we can cancel out if we divide out the G's, we have R1 M1 minus R2 M2 equals 0. Okay, I'm going to erase this now. Suppose we know that R1 is 10 meters, and we know what M1 is and M2, and we want to solve for R2. We could easily do that. R1 M1 equals R2 M2. If we needed to solve for R2, we'd simply say R2 equals R1 times M1 divided by M2. So essentially, what this allows us to do is when you have a seesaw situation and you want to balance out the seesaw to make it in static equilibrium, this gives us the physics equations to allow us to do just that. We're balancing out these two torques, the torque on one side versus the torque on the other side. There are some problems in the back of the book in this. So this would be how this is done. I won't go through I won't plug any numbers in this, but if we move on, there's one more type of problem, well maybe two more types of problems that we want to solve, and that would be, if we look on page 1, it starts on page 197. That's called Objects on an Inclined Plane. And the main thing, the main physics gets involved when page 198, 199, on page 200, 201. And then there's a problem on page 201 and 202. This might be considered about the most complicated problem in this book, in this chapter. And it can be a little complicated, so we'll spend a little bit of time going over this. But it's basically a mass sliding down an inclined plane where there might be friction. Okay, if we have an inclined plane, basically it's like we have a piece of wood, like a 2x4. Okay. And we put a block on here, and this 2x4 is at an angle, and it's some angle theta. And we put a block on here, and we allow it to slide down. Now there may be friction on here, and there may be friction, and there may not be friction. So we want to solve actually both cases. Let's suppose for right now actually that there is no friction. This is the we have a mass. Here's our mass. I'll write it as M. Okay, and it's on an inclined plane. We'll call this is a inclined plane type of problem. This is probably, you might think of this as the most difficult problem in this chapter. But it's not too bad if you approach it in a systematic way. Okay, again, we break things up into two sets of x and y problems, horizontal and vertical. But in this case, again, what we would do is we would normally say we want to look at the sum of the forces in the x dimension and then the sum of the forces in the y dimension. But when you have an inclined plane problem, the mass can only slide up and down this way. It can't go vertical. It can only go up and down one way. So what we want to do then is we're going to rotate our axis, and we're going to say the sum of the forces along the plane and the sum of the forces that are normal to the plane, that are normal to the plane. It's much easier to solve this way because the block can only move in one direction. The block can only move parallel to the plane. Okay. The block is not moving this way, up or down this way, normal to the plane. So we can say that the sum of forces normal to the plane are actually 0 because the block is not moving in this direction. And so this is the benefit. Basically, we're rotating the way we look at this block. Okay. So let's look at the sum of the forces. The sum of the forces that are parallel or along the plane, parallel to the plane. Again, the plane is this line right here. We take now the mass, the weight. I'm going to say that the weight is right here, and the weight acts down. I'm going to put the weight all the way coming down this way. This is the weight. Okay, now, if this angle here, if this is theta, okay, what we're going to do is we're going to break this weight up into two dimensions. One that's parallel to the plane and one that's not. So we can take this weight and we're going to break it up this way to a force that's parallel to the plane, and then to a force that's perpendicular to the plane. Okay, so I'm going to call this, I'll call this weight that's parallel, and then I'll call this weight that's perpendicular. Now, we can still do this. Remember, we can break any vector up into a vector quantity or vector components. It's simply we're taking the weight and we're simply breaking it up into quantities, vector quantities like this. So basically the full weight is still the sum of the parallel plus the sum of the perpendicular. So we haven't changed the weight. Remember, when we do this, we're allowed to do we can take a vector and we can break it up any way we want to. What we're doing here is we're breaking it up into a force that's parallel to the plane and then a force that's normal or perpendicular to the plane. Okay. Well, let's go ahead. I hope you can see this diagram here. Well. Okay. If this is a right angle, okay, if this is theta, then this angle right here I'm going to call alpha. If this is alpha, then this is theta also. Okay? Okay. So, and let me see, if we, okay, we can also, and we can, so, yeah, I'll do it that way. So this, the forces, the sum of the forces, this is W here. The sum of the forces that are parallel is this parallel force is acting this way, and that's the sine that the parallel is going to be this times the sine of this angle theta. And if you can see, if this is the full W right here, and this is theta right here, then this parallel is W times the sine of this angle. I hope that's clear. Okay, and this is of all, if there's no friction, force, then the only forces that acts along the plane is this, W parallel, and that equals to mass times acceleration. So we would say that W, the weight times the sine of this angle, equals to the mass times acceleration. Now the weight here, we know that the weight is simply mg. So we can also say that mg times the sine of this angle equals ma. Now a is the acceleration. A is simply the acceleration along the plane. Notice that the masses cancel out. These two masses are the same, which means that the acceleration that the mass actually feels is gravity times the sine of the angle. Okay, so if the angle is a small angle, if the angle is a very small angle, then the sine of the small angle is going to be a very small number, and it accelerates quite slowly, which you already know. If you have a low ramp, an object will accelerate, but quite slowly. The steeper you make it, the faster it will accelerate. And if this is 90 degrees vertical, the sine of 90 degrees is in fact 1. So that just means the acceleration is the acceleration of gravity, which we know. Now, let me say two things about this. I'm going to erase this right here. If you look at the diagram in the book, sometimes it might help. Another way to look at this diagram, I'm going to redraw this diagram, but in a slightly different way, because it might be that some of you might see it a little bit differently. If this is the mass, here's the mass, and we take this, here's W, whoops, W acting down. Okay, I'm going to draw it, this is a right angle here. In this case, I'm going to break it up the same parallel, but in this case, I'm going to draw it like this. I'm going to say this is the parallel, and this is the perpendicular. Okay, so it's really the same thing. I just drew it over here. This is the perpendicular. It's acting perpendicular, and this is the weight acting parallel. It's parallel to here. Some of you might be able to see it easier this way. If this is angle theta and this is angle alpha, where alpha plus theta equals 90 degrees, then that means that this angle is also theta. Okay, so if this angle is theta, then what we call W parallel is the full W times the sine of that angle. And you might see it easier that way. Yeah, we had the same thing over here, W times the sine of the angle. But here, this angle may be easier to see. Okay, I just wanted to show you that. Now, suppose, however, I'm going to keep with this right diagram. Suppose that we now have friction, where not only do the sum of the forces in the parallel are, we have the weight parallel, which acts down the plane. It acts this way, down the plane. But opposite act, if we have friction, if there's friction right in here, okay, the friction acts opposite to the direction that the mass moves. If the mass is accelerating this way and is moving this way, the friction acts opposite. So we would have to subtract a friction, which acts in the opposite direction. And the sum of those, the sum of the weight, the parallel action of the weight minus the friction would be equal to the mass times acceleration. Now, remember back to last chapter to how we calculate friction. The friction here, friction equals your coefficient of your friction coefficient, and it could either be the static or it could be the kinetic friction. Let's just say the object's moving. So let's say let's say the object is moving, so we're in a moving situation, so we're looking at the kinetic coefficient of friction times the normal force. Now, what is the normal force? The normal force is the force that acts normal to the surface, right here. Okay, remember when we had the situation where back in chapter 5, where the plane was horizontal, the normal force acted up. Well, in this case, the plane is tilted. The normal force acts parallel to the surface. So it would be the force that essentially that the surface here resists this perpendicular weight. So, okay, so we're going to say that this, and again, the weight per parallel is equal to the weight times the sine of the angle. So we have weight times the sine of the angle minus the coefficient of kinetic friction times the normal force equals ma. Now, how do we know what the normal force is? We know what the normal force is by looking at the second equation, the sum of the forces that are perpendicular, can't spell that, to the plane. Okay. The first equation was the sum of the forces that are parallel to the plane. The second equation was the sum of forces that are perpendicular to the plane. So in this case there are two. We have the normal force, which acts up, we'll say. So we have the normal force, which acts up, and acting down is this parallel weight, the perpendicular weight, which acts in the opposite direction, and that equals, the sum of those equals 0. We know it's equal to 0. The mass does not accelerate up or down this way. It does not accelerate in or out of the plane. It moves parallel to the plane. So therefore, we can say that the sum of these forces equals 0. So the normal force is equal to the weight, normal force minus the weight. Well, the perpendicular weight, this force here, would be the weight times the cosine of this angle. It's this weight times the cosine of this angle. So it's down here, it's a weight times the cosine of the angle equals 0. It allows us to solve for the normal force. The normal force is therefore, I hope you can see this, is the weight times the cosine of the angle. Okay? So we're going to take this, the idea that I'm going to erase this right here. The second equation allows us to solve for the normal force because we now know that the normal force is equal to the weight times the cosine of the angle. Therefore, we know that the friction is equal to the kinetic coefficient of friction times the normal force, the weight times the cosine of the angle. So we can plug this into the first equation. So now that we know what the friction is, we can take that and plug that right into here. Okay, and we have, I'm just going to repeat this right here, coefficient of friction times the weight times the cosine of the angle equals mass times acceleration. I'm going to go ahead and put in what the weight is. The weight is simply mg, so we have mg times the sine of the angle minus the kinetic coefficient of friction times mg times the cosine of the angle equals ma. Notice that very conveniently there's a mass term in each of these three terms which we can divide out. Okay, which leaves us with the fact of g times sine of the angle minus the coefficient of friction times the cosine of the angle equals the acceleration. We can now come in here and say that if we plug in the angle and we know what the coefficient of friction is, we can solve for what the acceleration will be. So I hope this is clear. At this point, we have an equation. Remember, we really started with two equations, that the sum of forces that are parallel to the plane, going this way, you have the weight acting parallel, which is this weight here, acting parallel, acts down the plane. We have friction that acts up, or that acts in the opposite direction. The sum of those forces equal mass times acceleration. The friction is the coefficient times the normal force. We use the second equation, the sum of forces perpendicular to the plane, to calculate what the normal force is. The normal force has to be this weight perpendicular. The weight perpendicular is the weight times the cosine of this angle. The weight times the cosine of the angle. So it allows us to calculate quite easily what the friction is. We plug that in here into this equation. And it allows us, when we simplify things, to solve for the acceleration that the mass feels. If you might even have a problem where you know what the acceleration is. You have a block up here and set up at an inclined plane at a certain angle. You measure the acceleration. It would allow you to back calculate what this coefficient of friction is. Now, if the object was stationary and wasn't moving yet, then we would say it would be the static coefficient of friction. It was just about to move. And what we had as this, instead of the kinetic coefficient of friction, we would simply have the static coefficient of friction, which would mean that the object hasn't moved yet, but it's just about to move. It's overcoming the static coefficient of friction. So this gives you, hopefully this gives you a systematic way of solving this type of problem. This is on page 198, 199, 200, and which takes us up to page 202 and 203 and 204. And we will end with the problem that they have on page, let's go ahead and look at the problem they have on page 203. It looks like a complicated problem, but it's really not too hard. Okay, on page 20, let's see. If we look at it, the example 6.6 on page 203. Actually, let's look at page 205. 205, and here's a problem. It says on your own. It says, and let's go ahead and solve this problem, and it's exactly just like the other problem on page 203. The problem is this. A girl is riding, there's two boxes. There's, we'll call it M1, which is 322 kilograms. And the girl is pulling this on a bicycle. She's pulling this with a rope. And the question is, what is that force in that rope? And this weight, which we'll call M1, is tied to another mass, which we'll call M2, which is 245 kilograms. And what they tell you what the tension in this rope is 45 newtons. The tension in this rope is 45 newtons. And the question is, what force must the girl pull this way? She's on a bicycle. So what is this force going this way in order to, let's see, two boxes are attached to a string that can withstand a tension of 45 newtons before it breaks. So what is the maximum force? What is the maximum force that she can pull her bike with without breaking the string? Okay. Well, how do we solve this? Okay, how do we solve this kind of problem? When you have a problem like this, again, it's a problem it's a one-dimensional kind of a problem. There's a road here or a surface. We're going to say that there's no friction. The assumption here is that there's no friction. We could solve it with friction, but I think the problem says ignore friction. Okay. When we have two masses, we can separate these two masses. But first, the important thing to realize is when this thing is moving, both these are moving at the same speed. Okay, both of these are moving at the same speed. So let's look at this first one. If I draw a little circle around here, around M2, what we have is that here's M2. M2 feels a tension on it. That's T1. Okay, so let's do Newton's second law applied just to here. What we have, remember, we have the sum of the forces equals mass times acceleration. There's only one force on this, and what we're going to do is of course there's a weight acting down, but this will be the force in the x direction that we're looking at. So there's a tension acting to the right, this T. So T equals mass m2 times acceleration. We know what this T is, so we can solve for what the acceleration is. So we have the acceleration equals T over m2. T is 45 newtons. m2 is 245 kilograms. So that means that the acceleration is 45 divided by 245, 0.18 meters per second squared. Okay. Now notice, if this has a certain acceleration, these two are connected, so both of these boxes have the same acceleration. They're all moving